afternoon, everybody. Welcome to this presentation. I'm Eveline Volcke. I'm a professor here at the Faculty of Bioscience Engineering of Ghent University, more specifically at the Department of Green Chemistry and Technology. And it is my pleasure to talk to you today about reducing the carbon footprint of wastewater treatment. And we will do that as engineers using innovative technologies and specific engineering tools we have at hand. First talk about carbon neutrality, and more specifically about greenhouse gas emissions from wastewater treatment. A concept that you have heard is net zero. It was defined by the United Nations, and it means that we want to cut carbon emissions to a small amount of residual emissions that can be absorbed and durably stored by nature and other carbon dioxide removal measures, such that we have zero left in the atmosphere. And there are some specific targets that we want to reach, such as limiting the global temperature increase to 1.5 above pre-industrial levels, or achieving net zero by 2050. Okay, we need to reduce greenhouse gas emissions, and we need to do that from different sectors, also from wastewater treatment. And there are many efforts in this way. One of them is through the IWA, International Water Association Task Group, greenhouse gas emission modeling and quantification. Greenhouse gases come from all types of industries. They also come in different types, and some greenhouse gases are more strong than others. For instance, if we take CO2 as a reference, it has one global warming potential over 100-year horizon. There's also methane, which is about 30 times stronger, and N2O, which is almost 300 times stronger. Good. And several utilities have committed to reach the net zero target, and they are doing worldwide efforts in this respect. Utilities have started to do greenhouse gas emission reporting. And they make a distinction between the Scope 1 emissions, which are the direct emissions from the processes, such as methane and N2O. If I look at that for wastewater treatment, but also indirect emissions, which are associated with the purchased energy, the typical CO2 emissions from energy consumption, and then also Scope 3 emissions, which are value chain emissions, may come from the upstream activities, but also from the downstream activities, including also transportation. For wastewater treatment plants, if we talk about greenhouse gas emissions, we typically look at three different components, being methane, which is a Scope 1 component. Where is methane formed? Methane is formed everywhere where we have anaerobic conditions, such as it's present in the sewer, and it can be present in the sludge treatment, can be formed in the sludge treatment train. Then also N2O. Call it in Dutch lachgas, nitrous oxide in English. It's mainly formed during biological nutrient removal, so in the denitrification process and also in the nitrification process. And then we also have CO2, but we do not look so much at the CO2 which is released during the biological conversions, because we consider that short cycle CO2, so it doesn't count. It's mainly the CO2 which is associated with the energy consumption, which is mainly for aeration. Okay, so let's now use our engineering toolkit to quantify greenhouse gas emissions and to try to minimize that. What do we have? Well, we have off-gas analysis. So we have an off-gas analyzer with which we will measure certain components in the gas stream. That's nice. We also have mass balances that we can set up, one of the most important tools for an engineer. Mass balance simply states that what comes into a system, a certain mass, overall mass or mass of a specific components, needs to be equal to the mass that goes out of the system plus what is converted in the system. And then you can also combine different tools, and we will gain even more insights from that. And this is what I want to demonstrate to you today. So let's start with off-gas analysis. What is that? It's simply measuring concentrations in the gas phase of a wastewater treatment plant, for instance. That is easier said than done. It's nice if the plant is covered, and then you can have some exhaust pipe somewhere and directly connect your gas phase analyzer to that. But not all plants are covered. And in that case, you then need to make a representative sample, for instance, with a floating hood. You take a gas sample, you send it to an online gas phase analyzer, and that can measure N2O and methane, besides other components. Typically also oxygen and CO2 are measured. Let's say we are interested now in the N2O and the methane. What is the advantage also of gas analysis compared to liquid phase measurements? That is that you do not need chemical reagents, as is the case with certain online liquid phase nutrient sensors. You can more easily take a representative sample from a gas phase than from a liquid phase, because the gas phase is typically better mixed. And also you have typically also less maintenance, because the gas phase is cleaner than the liquid wastewater phase. We have been involved in the first time long-term online monitoring campaign on a municipal wastewater treatment plant, a full-scale plant, a conventional activated sludge system. That was over 15 years ago. It was a plant in the Netherlands. We have measured for 16 months. An important advantage was that its plant was fully covered. We have measured N2O, methane, CO2. We did not, well, we measured it, but as I told you already, it was short cycle CO2, so it's mainly the CO2 which is related to the aeration, which is important there. Here are the results for N2O. You see here the variety, the dynamics over 16 months. And you see indeed that there is a very high seasonal and also diurnal variability. We have studied this in detail, also looked at influencing factors. We have also thought of how do you actually have to monitor to be able to quantify the emissions in an accurate or reliable way, because you're not able to go for an online monitoring at every plant. And there we have also given some recommendations for sampling. For instance, that is absolutely necessary to sample on a long term if you want to quantify the emissions, if you want to quantify the carbon footprint. It doesn't necessarily have to be online. Grab samples can do as well. But if you want to identify the mechanism, then you need to do online samples. And we have also given some guidelines on how to sample, how to measure, to have a certain precision. If you want to have a certain accuracy for the emission factor, how many samples do you need to measure, and how long should your sampling campaign take? That was very interesting, and attention for N2O emissions from wastewater treatment plants has really increased since then. And while everybody was starting to do measurements to quantify N2O, we also looked at methane. And we looked at this same plant. Here you have the process scheme, and in color you see the biological reactors. The green reactors are plug flow reactors, and the blue reactor is a carousel reactor. That is good. All the other units were covered. All units were covered, also these biological reactors. But from all the other reactors, the off gas was withdrawn and was then sent to this blue unit, the carousel reactor, and then also to a air treatment unit. The air from the other biological reactor was also sent through the off-gas pipe. And there, that gave us interesting options to do online gas phase analysis directly on what came from these two reactors. Besides, for every unit process, we also took liquid and gas grab samples, and we made mass balances. And this has allowed us to quantify all of the methane mass flow rates over this whole process scheme. So you see some numbers here. The numbers indicate the mass flow rates in kilogram methane per hour. And what was interesting was to identify what were the main sources of methane emissions. And we saw that 25% of all of the methane emissions in the plant were traced back to the sewer system. So they were actually formed in the sewer and they entered the plant. 75% of the methane emissions came from all the unit processes associated with sludge digestion. Sludge digestion, which we implement with the aim to produce biogas, which should be a renewable gas, and you want to save on CO2. But we have to take care, that's what we showed here, because if you do not operate these processes well, you risk that you have more methane emissions from sludge processing than the CO2 equivalents that you would actually save using this biogas as a renewable resource. There are, of course, possibilities to withdraw this off gas and to make sure that it does not escape to the atmosphere. A very interesting finding is that we also saw that there was a methane sink in the process. 80% of the methane that entered the biological reactor was converted, disappeared. And this was done biologically through methane oxidizing bacteria. There then we applied a mathematical model based on mass balances to see how we could optimize this process and what would be the influence of the reactor design and operation. Here you have the overall carbon footprint of the plant. And you see that for this plant, at least, nitrous oxide emissions were very high, almost 80%. Methane emissions were also higher than the CO2 emissions. So both Scope 1 emissions in terms of N2O and methane were higher than the CO2 emissions which were associated with energy. If we looked at the emission factors, because greenhouse gas emissions are typically expressed in emission factors, then these emission factors, amount of methane emitted per kilogram influent COD and nitrous oxide emitted per kilogram of influent total kLDAR nitrogen, both of the emission factors were higher than the reference values which were indicated at that time by the IPCC, the International Panel on Climate Change. Okay, so this was a long-term study on a conventional wastewater treatment plant. And we demonstrated that we can use our engineering tools, the off-gas analysis and the mass balances to do something, or to say something about that, and also to propose some mitigation measures. What if we now use a different technology, an innovative technology, such as, for instance, an aerobic granular sludge reactor? Aerobic granular sludge reactors are a true revolution in wastewater treatment. Let me first point out how they relate compared to the conventional wastewater treatment plants. In conventional wastewater treatment plants, we have removal of carbon, nitrogen, and phosphorus components, and that takes place in different reactor compartments. We then need to pump the wastewater from one compartment to another in order to establish all the required conversions, and that will cost us some pumping energy. The bacteria that purify the sludge, that purify the wastewater, grow in flocks. And these flocks are only slightly more heavy than water, which makes that they settle very slowly. And it takes a long time to separate them, the bacteria, from the purified effluent. Here you see a bucket of mixed liquor. After 5 minutes of settling, and you see that you hardly have any clean wastewater. Then there is a new technology, and there we were able to grow bacteria in granules. And the removal of carbon, nitrogen, and phosphorus takes place in different zones of a single granule. So you don't need to pump around the wastewater. Everything takes place in one single reactor. The bacteria grow in granules, and granules settle faster. They are heavy. They will settle better, and you can separate them actually in the reactor itself. You do not even need settlers anymore. So you save on energy for pumping, and you save on settling. Footprint of the installation. As a result, aerobic granular sludge reactors are compact installations. They use up to 75% less space than the conventional activated sludge treatment, They use up to 50% less energy and result in 30% less investment costs. Moreover, they also have specific advantages in terms of resource recovery. For instance, there are certain polymers that can be gained, such as the Comera, which is branded, and it is used as a biostimulant and also as a flame retardant. And there's a lot of research ongoing on that. But now, how about the greenhouse gas emissions? How about the carbon footprint of these type of reactors? Well, we talk about compact installations and resource recovery potential. So that indicates that in terms of scope 3 emissions, there must be something to gain. If we say there's less energy use, that points to the scope 2 emissions. But how about the scope 1 emissions, N2O and methane? Let's have a look. Starting with N2O. We did not measure N2O emissions from granular sludge reactors ourselves, so I refer here to a study that was done by colleagues in the Netherlands. They did a 7-month measuring campaign, and they found that the emission of N2O from aerobic granular sludge reactors is comparable with the one from continuously fed activated sludge plants, so the conventional plants that have low emissions, because there are a lot of different plants and the emission factors vary a lot in literature. In all the studies that have been done, also over time, I mean, this is something which cannot be quantified just as such by a single number. But the measured value was comparable to these continuously fed activated sludge plants, and it's also comparable. Well, I compare it here also with the IPCC. The IPCC value in 2006 was estimated relatively low. They revised it in 2019, and then it became 30 times higher. So, which also indicates that there's a lot of uncertainty. Aerobic granular sludge reactors are operated in a batch-wise mode. They are not continuously fed, and that could also give a certain dynamics. But if you compare their behavior to conventional SBR systems, which are also cyclic systems, the emission from aerobic granular sludge reactors is lower. These colleagues did a study over 7 months, and they related the N2O emissions to the temperature, and they saw that the variability of the emission increased in the months where there was a lower temperature. And also, they pointed out that it would be possible to reduce the emissions by adequate process control. And that we like to hear as an engineer, because we like to improve things. We looked into the fate of methane in aerobic granular sludge reactors. As I indicated before, there are 2 main sources of methane, methane coming from the sewer and methane which is related to sludge treatment. Let's focus now on what happens to the methane that comes from the sewer. The methane that comes from the sewer enters the wastewater treatment plant through the pre-treatment units, screen, grid chamber, primary settler maybe, and we have indicated, we found it ourselves, as I already told you, that a lot of this methane can be converted in the biological reactor by methane oxidizing bacteria. Very nice. This was also confirmed not only by us, but also by other researchers. And now we'd like to know if that is also the case in aerobic granular sludge reactors, because it's very important. Will methane also be oxidized here, or will it rather be stripped from the reactor? And how can we minimize the methane emissions? Well, there are a few reasons why the behavior of aerobic granular sludge reactors is different from the one of conventional activated sludge systems. First of all, aerobic granular sludge reactors are operated in a cyclic way. Feeding and aeration does not take place at the same time, and this may have some implications. Secondly, the bacteria grow in granules and not in small flocks, so there is more diffusion resistance. This means that the methane may need to diffuse into these granules, and it takes more time before it gets to the methane oxidizing bacteria that can convert it. Third, Granules stay relatively long into an aerobic granular sludge reactor compared to the residence time of flux in an activated sludge reactor. If they stay longer, you may think there is more time for methane oxidation. And last, the aerobic granular sludge reactors are typically tall reactors. This makes that the gas bubbles stay for a longer time in the reactor. They will also be more saturated with methane. That can have an influence on the methane stripping. Also, the pressure at the bottom of the reactor will be higher. That makes that the methane more easily stays into the liquid phase. Altogether, there are 4 effects that could influence the fate of methane when we switch from activated sludge systems to aerobic granular sludge systems. In order to investigate these influencing factors, we built a model, simple model based on mass balances. A mass balance for the methane entering the reactor with the influent, exiting the reactor with the effluent, methane which is emitted to the atmosphere, and methane which is taken up by the methane oxidizing bacteria. Also, we made a mass balance for the methane oxidizing bacteria, describing their growth, decay, and the wasting of sludge. And here you have the result. This graph shows now for a conventional activated sludge system how much of the methane that enters the wastewater treatment system, how much of the methane that enters the biological reactor is oxidized. And for conventional activated sludge, this is very good. At least in our model, it's 85%, depending on the influent methane concentration. If we look at the aerobic granular sludge systems, it's quite disappointing. It's very bad, actually. Hardly no methane is oxidized. And how come? This is exactly because the feeding is separate from the aeration. So what happens? You first have a feeding phase. Methane concentration builds up. There is no oxidation because there is no air at this moment. And at the moment that you turn on the air, all the methane is stripped from the reactor. So if we look at, that was the effect of the separate feeding and aeration, it's bad. If we look at the fact that the bacteria grow in granules rather than in flocks, it's also negative. I will not give all the details here. The longer residence time indeed resulted in some improvement. The fact that the reactor is built higher hardly makes an impact because methane is so poorly soluble in water that it hardly has an effect. So that doesn't look very good for aerobic granular sludge reactors in terms of methane emissions. So what should we do then? How to reduce the methane emissions? Well, what we can do is we can cover the pretreatment units. What we can do is cover the reactors itself. This is more easy to do for aerobic granular sludge systems than for conventional wastewater treatment systems because they have a relatively smaller footprint. And then with that air, you could feed that air containing methane, for instance, to the cogeneration unit and use it as combustion air there. That could be an option. So what I told you so far is some insights from model-based assessment, insights on the fate of methane in granular sludge reactors compared to activated sludge systems. But if you really want to know how much methane is emitted from these reactors, of course, we should measure it. And this is what we did as well. It was a short measurement campaign, 4.5 days. And then we saw it was actually, that at that time at least, not too bad. The methane emissions were comparable to the ones of activated sludge plants. But this still needs to be confirmed by long-term measurements on these type of systems. Okay. Let me go back to my engineering toolbox, the off-gas measurements and mass balances. I want to step aside for a moment and show you what we can do with this wonderful combination. it was indicated many utilities want to quantify greenhouse gas emissions. So they buy this equipment, they are measuring gas phase concentrations of N2O and methane. And what I now want to tell you is that while you are doing that, please also measure oxygen, CO2, and then make some smart calculations, and you will get so much more. We can learn a lot from the composition of a gas bubble while it is rising in the wastewater treatment reactor. An air bubble starts with an air bubble which has the same composition as air. It rises, and while it rises, the microorganisms convert all types of components. They consume oxygen, they produce nitrogen and CO2, and that makes that the composition of the air bubble changes. Oxygen concentration is depleted, CO2 and nitrogen concentration increases. And you can measure all of that, so you actually get a footprint of what happens in the installation, besides measuring N2O and methane as greenhouse gases. If we measure the gas phase concentrations and we also measure the gas flow rates, we can make a gas phase mass balances, and we can calculate liquid gas transfer rates, such as an example here for the aerobic granular sludge reactor, which is operated in a cyclic way. It's very interesting to see that the oxygen absorption increases over a cycle. Also, CO2 emission increases over the aeration phase. Both of them, they are coupled because they are connected through the conversion of organic material. Also, methane emission profiles can be seen, and N2O emission profiles. The methane emission profile here is the typical stripping profile. The N2O emission profile is different. It results from biological production. The whole footprint. We can calculate liquid gas transfer rates for any components. We can also do it in specific for oxygen. Measuring the oxygen gas phase concentration, measuring the gas flow rate, making a mass balance for oxygen in the gas phase, and then we can calculate the oxygen liquid gas transfer rate, also termed the oxygen transfer rate. And from that, we can calculate some parameters, such as the oxygen transfer coefficient and the oxygen transfer efficiency. You do not necessarily have to go into the details of the formula, but please keep in mind that both the KLA and the OTE are parameters that give an indication of the oxygen transfer efficiency, of the aeration efficiency. The higher they are, the better. And we were able to calculate these characteristic parameters for an aerobic granular sludge reactor, and we saw, this is quite interesting, that they increased during an aeration phase. Blue is the aeration phase. So that means that the aeration performance increases along the cycle. Of all the oxygen that you put in the system, more will be used efficiently along the aeration cycle. I will come back to this. But first, let me show you what you can do even more with these measurements of the off-gas and with mass balances. So we already indicated we can calculate liquid gas transfer rates. We can do it in specific for oxygen. We can calculate the KLA. We can relate the KLA of oxygen to the KLA of N2O and methane, oxygen transfer efficiency. And then when we know those, we can actually recalculate with some mass balances the liquid phase concentrations of N2O and methane without measuring. So we now have a technique to quantify the concentration of N2O and methane in the liquid phase without needing liquid phase sensors. Simply using gas phase device, making use of the relation between the KLAs, DO measurements, and making some mass balances. And mass balances can give us even more. So let's do some off-gas analysis and measure, for instance, oxygen. Let's also make some typical liquid phase measurements, quantifying the influent organic carbon, influent nitrogen. Then we make some mass balances. Well, this will allow us to close those balances, and we can calculate variables that we actually cannot measure. Such as the amount of oxygen that is used for organic carbon conversion and the amount of oxygen which is used for nitrification. So this gives us a very nice toolbox, a way to calculate certain KPIs in wastewater treatment. Imagine that you could do this for your plant. You do it over time, you do it for several plants, and you compare the performance. You can actually benchmark them. Good. So far for toolkits. Let's go back to the granular sludge reactors. We have already discussed N2O emissions, methane emissions. Let's now say something about aeration energy. As I already indicated, aerobic granular sludge reactors are operated in a batch-wise manner. So we have several phases: a feeding phase, an aeration phase, and a settling phase. And feeding takes place together with the draw phase. So the influent is fed at the same time that the effluent leaves the reactor at the top. It's supposed to be a perfect plug flow. I already indicated to you that for aerobic granular sludge reactors, we do not need pumping. We also hardly need mixing. We don't have mixers there. So that means that there's a lot less energy consumption, but all the energy which is consumed for aeration. So if we want to save further on the energy consumption of anaerobic granular sludge reactors, we need to save on the aeration. So the question is, how can we optimize the aeration? What we did is we analyzed the data of 175 batch cycles of such aerobic granular sludge plant. We studied the off-gas measurement, the liquid phase measurement, and we calculated the aeration efficiency over all of these cycles. Remember, there is a certain airflow rate, a certain amount of oxygen that is given by the blower in the wastewater treatment plant, and there is a certain amount which is transferred, actually taken up in the reactors. Every difference between that is a loss. And we have seen that over the aeration time, as the aeration phase proceeds, the oxygen transfer efficiency, the aeration efficiency increases. This is very interesting to see. So this was a constant that we have seen studying all of these cycles. And actually, it is also very similar to what has been observed in a conventional activated sludge process in a spatial dimension, not in a time dimension. We were able to trace back this behavior to the degradation of surfactants, soluble biodegradable organic carbon. The surfactants actually block the access or the diffusion. They attach on the air bubble, and it's more difficult for the oxygen to get out. That's how you can see it. You can also describe that mathematically. And this gives maybe some opportunities for process optimization. So we studied this behavior. We made a mathematical function to describe the behavior of the aeration efficiency along with the concentration of these surfactants. We put that in a model, and we were able to simulate the profiles of an aerobic granular sludge reactor. We also showed that it was actually necessary to quantify this specific dynamic aeration efficiency behavior. And we used that model in a simulation study, trying to optimize the behavior of an aerobic granular sludge reactor. We played here with the volume exchange ratio. So what is the volume exchange ratio? Each cycle, you take in an amount of wastewater. Not 100%, because, as I already told you, you have simultaneous feeding and effluent withdrawal. So there's an amount that you can feed the reactor with. So the volume of the fresh water compared to the whole volume of the reactor is called the volume exchange ratio. And we found that there is an optimal volume exchange ratio, leading to the highest possible treatment capacity. You can think of this yourself. If the volume exchange ratio is low, the lower it is, the relatively small the reaction time is compared to the feeding and settling time. So there you lose on the treatment capacity. That's logical. But you would not have expected maybe that there is also a maximum. And that is because this dynamics in the aeration efficiency. If the volume exchange ratio is too high, you have a very slow or a relatively slower increase of the aeration efficiency over the cycle. And that leads to this optimal volume exchange ratio. So all of this information helps to optimize the performance of the reactor and to find the optimal treatment capacity. And then I want to take a final minute to talk about the importance of data. We do not only want to have data, we also want to have more information. We all need data, not just data, but also good quality data for decision-making, performance assessment, and all types of things. And this is very important. We often forget, especially as modelers, we often forget we are so blinded by our great model that we have made that we sometimes forget that if the data that we put in is garbage, what we will get out will also not be very good. And therefore, we always need to take a moment in every project to look at the quality of our data. And we therefore apply a tool called data reconciliation. It's actually a combination of mass balances and statistics. And it can lead to accurate and reliable data. It allows us to detect gross errors in data sets. It will also allow us to improve the accuracy of measured variables. And it's interesting to know that if we have off-gas measurements, we can add even more value to that. It allows us to calculate even more variables that you cannot measure. Okay, that brings me to my take-home. First of all, wastewater treatment plants emit greenhouse gases. We are aware of that, we can quantify them, and using off-gas analysis and mass balances, we have also found ways to understand it better and to mitigate their emissions. We have looked in particular to the carbon footprint of aerobic granular sludge reactors. We've seen that their NTO emissions are comparable to activated sludge systems. Their methane emissions seem hindered by separate aeration and feeding. We could cover those installations maybe. The CO2 emissions as such are lower than for activated sludge systems. Aeration energy dominates, and we have gained fundamental insights into aeration efficiency, which have led to further optimization. We have a nice toolkit at hand, off-gas analysis and mass balances. They allow us to follow the aeration performance, leading to energy savings. We can quantify different parameters. They could allow us to quantify greenhouse gas emissions and establish footprint reduction. We quantify emission factors. We can calculate liquid gas transfer rates and measure dissolved concentrations. And finally, combining mass balances and off-gas analysis leads to better quality data and more information. I want to acknowledge here all the people with whom I have collaborated to come to all the findings presented. They are essentially the co-authors of these articles. And I want to thank you for your attention.